Welcome back. In this video, we'll be learning about one of the simplest yet powerful predictive modeling technique known as KNN, which is short for K nearest neighbors. This algorithm is also known as the lazy learning algorithm, and by the end of this video, you'll understand why. Let us now look at an example to understand this better. Here we have a classroom, and suppose you are the class teacher. Now, your classroom has a maximum strength of 9 students, and at present, there are only 7 students enrolled in the class. During our school days, we always preferred to sit with our friends who have the same interest as ours. And of course, our teacher could easily identify the groups in the classroom. Now, in your classroom, there happens to be 2 groups of students. The first of them are more of the studious ones, spending most of their time in the library reading books or novels, etc. The second group here are the students who are interested in sports like cricket and football, and they spend their free time discussing about the upcoming matches. Now there's a new admission in the class, and this new student, after a brief interaction with his classmates, chose to sit on the rightmost bench. A week later, the principal asks you about what are the interests of this student outside the classroom. Since you did not have any time to interact with the student personally, you observe the group of students he spends most of his time with, and you report back to the principal. You can confidently say that this new student is more inclined to reading books and novels in his spare time rather than watching sports online. So you did not spend any time in observing the student's activities or conversing with him personally, but you simply made conclusions based on his neighbor's behavior. And that is the reason it can be termed as a lazy learning approach. The trick which you used right now is the intuition behind the KNN algorithm. Now, in the KNN algorithm, the predictions for the new data points are made by looking at its neighbors. We'll go into more detail of this algorithm in the upcoming video, but for now, let's just go through the concept we learned. So, KNN algorithm has no learning process, and all the magic happens when the predictions are made on the basis of its neighbors. Hence, this algorithm is also known as the lazy learning algorithm. It is one of the simplest machine learning algorithms. Let's say we have some training data. Now in KNN algorithm, we start with plotting the training dataset. So this plot here is from the Titanic dataset, which we have explored rigorously in the past videos. Now for simplicity, I am considering only 2 features here, the age and the fare. In this case, our target variable is survived. It is represented by the blue and green color. So once we have the training dataset, next we locate the new data point in the plot. We are showing it here with the star. This point has an age of approximately 45 and the fare of approximately 58 or so. Now we want to predict if this particular person with the given age and the fare will survive or not by looking at its nearest neighbors. Now the next step is to calculate the distances from all the points in the dataset. So the distance of this star from this point and all the points in the graph is calculated. Now let's assume the distances obtained are as shown in the list below. So the distance of this point from, let's say, here is 6, from this point is 2, and so on and so forth. Now we'll sort the list of these distances in ascending order. So here we have the distances in ascending order. And now we'll select the first k shortest distances from the list. So let's say for now, I want to look at the 5 nearest neighbors of this star. So I'll mark the first 5 values in the list. Now you might have a question about how or why did I choose the value 5. We'll discuss about this in the next video. For now, let's consider that we have the value of k to be 5. So if I mark 5 nearest neighbors of this point, it will be these points, right? So once I have the nearest neighbors, the final step is to make the predictions for the data point based on the neighbors. So we'll take a mode of the labels of the nearest neighbors. Here we have 4 green points and 1 blue point. In this case, the mode will come out to be green, which is 1. So we can conclude that this new point in the test data will have the target as survived. Now this is an important step, determining the category of the value of new instance depending upon the nature of the problem. If the problem is a classification problem, we assign the mode to the new instance, and if the problem is a regression problem, then we assign the mean to the new instance. So we have now learned the step-by-step procedure on how to build a KNN algorithm. Now we'll learn how to determine the right value of k for the KNN algorithm. The straightforward and probably the most commonly used method to determine the right value of k is the elbow method. But what is the elbow method? So you know what an elbow looks like in the normal resting position. It has an angle here. If you see in this image, when we go along the edge of the elbow, there is a sudden change in the direction. Now similarly, when we weigh the value of k, we obtain a graph similar to this. So let us see how to determine the right value of k using the elbow method. Firstly, we'll select a range of k values. Now note that the minimum value of k can be 1 and the maximum can be the number of data points that the dataset has. Secondly, we'll implement the KNN model for every value of k in the range we just selected. After that, we calculate the error generated by the model for every value of k and plot it. The plot would look something like this. Here we have the range of k values on the x-axis and the error on the y-axis. So looking at this graph, we select the value of k which has the minimum error, which here comes out to be approximately 10. Since this graph has the shape similar to an elbow, it is often known as the elbow curve. And this is used to select the right value of k. Now once we have the value of k, how can we decide which points are the nearest? So to determine the nearest points, we calculate the distances between points. And in this video, we'll cover the following 4 distances. Let's start with the Manhattan distance. The Manhattan distance is the sum of absolute differences between 2 points across all dimensions. Sounds complicated? Let's break it down. For now, we'll consider just one dimension. Now we have 2 points in this dimension, A and B, which has coordinates P and Q. Now how do you think we can calculate the distance between A and B? Quite simple, right? We can see the value of P to be 3, we have the value of Q to be 8, and we'll simply calculate the absolute difference, 3 minus 8, which comes out to be 5. Let's try another example. Here we have 2 dimensions, and we have the coordinates of A as P1, P2, and coordinates of B as Q1, Q2. How do you think we can calculate the distance between A and B in this case? Look at the definition more carefully. We can see that it is the sum of absolute differences between 2 points across all dimensions. So we'll take one dimension at a time. We'll first calculate the difference between A and B in this dimension and then in this dimension. So here we have the difference between A and B in this dimension to be Q2 minus P2, and we have in this dimension would be P1 minus Q1. And again we take the absolute differences. So if I plug in the values here, I'll have it 9 minus 5, and in this case I'll have 8 minus 5, and again the absolute value for both of these. So we have 3 plus 4 and the distance comes out to be 7, right? And similarly, if I take it to n dimensions, we'll calculate the sum of absolute differences between the points in all dimensions. So we'll take it to Pn to Qn, where n is the number of dimensions. Now I can write the same formula in this way, where we have the absolute difference between the coordinates P and Q, and we have I going from 1 to n, where n is the number of dimensions and Pi and Qi are the data points. But the Manhattan distance is not the shortest distance between 2 points. So we have another technique called the Euclidean distance, which calculates the shortest distance between the 2 points. Now recall this example from Manhattan. We calculated the distance in this way and we found out to be 7. Now what do you think will be the shortest distance in this case? It will be something like this line, right? So this will be the shortest distance. So can you guess the formula to calculate the distance between A and B? Remember the Pythagoras theorem? We had the value of D is equals to the root of A square and B square. So I've written the formula here. And if I plug in the values of A and B in terms of P and Q, I'll get it as P1 minus Q1 square plus P2 minus Q2 square and the complete root. So let's put in the values. We'll again get this as 4 square and 3 square, and we take a root of this. So it comes out to be 5. Now instead of 2 dimensions, if I calculate this for 3 dimensions, we'll have this as P1 minus Q1 square plus P2 minus Q2 square plus P3 minus Q3 square and the root of the summation. Now if I generalize this for n dimensions, we'll have the formula something like this, and we can write this again in a more simple form. So we'll use summation of pi minus qi square and the root of the summation. Here again we have the value n, which is the number of dimensions, and pi qi will be our data points. So we covered two techniques to calculate the distances, the Manhattan distance and the Euclidean distance, and here are the formulas for both of these. Now the same can be written in this form, where we have the value of k is equals to 1 for Manhattan distance and the value of k is equals to 2 for Euclidean distance. Now this is called the Minkowski distance, and here is the formula for the same. So all the techniques we covered right now are to calculate the distances between continuous variables. Now we have another technique called the Hamming distance, which is used to calculate the distance when we have categorical variables. So let's understand how this works. Hamming distance is basically the total number of differences between two strings of identical length. Now by identical length, we mean the number of variables in both the points should be the same. Let's look at a few examples. So for now we have one variable gender and we have three rows A, B and C. So I've converted the variable gender male and female into strings 0 and 1. Now in this case 0 and 1 do not have an order, so 1 is not greater than 0 and 0 is not less than 1. Now if I calculate the distance, I would see the number of differences between two strings. So simply we have 0 here and we have 1 for the ID B. So you have to check it in this way, that in this case, did the value change or is there a difference? Yes. So I would say that the distance between A and B is 1. And the distance between B and C is again 1 because one value has changed. And the distance between A and C will be 0 because there is no change in the value. You'll understand this better if we take multiple variables. So let's see another example. In this case, we have three variables: gender, marital status, and employment status. Now again, I'll convert these variables into numbers. So we have 0 and 1 for gender, male and female. Again, we have 0 and 1 for married and unmarried. And we have 1, 2, 3 for employment status. As I mentioned previously, these numbers do not have an order. We only look at if the values have changed or if there is a difference. So if I look at it in this case, we can say that the string for A is 001 and string for B is 102, and similarly for C it's 013. Now in this case, when we compare A and B, how many values in this string changed? So the 0 changed, yes. This value, no. And this value again, yes. So the distance between A and B will be 2. Now if I compare A and C, suppose, we have the first value 0 in both cases, so I say that this does not change. And this second value changed, yes. And then we have the third value that changed from 1 to 3. So again, we have the distance for A and C to be 2. Note that we did not take the difference here. So change of 1 to 2 was also considered as a change 1, and from 1 to 3 was again considered as a change 1. So these values don't really matter. So I hope you understood how the Hamming distance works. Now go ahead and calculate the Hamming distance between the points B and point C. So the distance-based algorithms take the distance between 2 points into account. Now for now we have just covered the KNN algorithm, but there are also other algorithms like k-means and hierarchical clustering which take the distance between points into consideration. Now these algorithms fail when the variables have different scales. So for example, if you have a variable income which may range from 0 to say 1 lakh, and then another variable age that might have a range from 0 to 80. So in this case, distance-based algorithms don't perform well. Now you might ask why. This is because there is a huge difference in the scale and the relative distance between the points change, which might lead to ambiguous results. So let's take an example. Suppose I have price on the x-axis ranging from 0 to 50 and distance in kilometers which ranges from 0 to 1, and I have the following points A, B and C on this plot. So here we have two features, price and distance. Now if we want to calculate the distance between these points, let's say we use the Manhattan distance. So what do we do in that case? We subtract P1 minus Q1 and P2 minus Q2 and take the absolute values and add these values. BA comes out to be 0.6 and BC comes out to be 10 units. Now we can clearly see that BC has a smaller distance than BA, but according to the calculation, it looks like BA is smaller than BC. So what's the solution here? Can we not use the distance-based algorithms at all? Actually, no. In this case, all we have to do is scale down the features and bring them to the same scale. So even if we have two features which have different scales, we need to bring them in the same range. So I have scaled down both the features in the range 0 and 1. Now if you calculate the distance, BA comes out to be 0.6 units and BC is 0.2, which seems fairly right. So this is one thing to keep in mind. Whenever you work with any distance-based algorithm, you must make sure that there is no large differences in the variables and ensure that you always scale your variables down and bring them to the same scale range. So we'll work with both classification and regression problems. Let's start with the classification problem. So we'll start with importing the required libraries. Here we have pandas, numpy and matplotlib. Matplotlib is used to plot the graphs in Jupyter, and we use %matplotlib inline so that we can see the graphs inside the Jupyter notebook itself. And then we import any warnings that we get. So let's run this cell. Now, once we have the required libraries, the next step is to load the dataset. Here we use the cleaned version of the Titanic dataset. So let's look at the first few rows, and data.head will give us the first few rows. So here we have the Titanic dataset, and in this case, we have the target variable as survived, where we want to predict based on the features of the person, whether the person will survive or not. Now, when I say the cleaned version of Titanic dataset, I mean that we have already taken care of the missing values. So we have imputed the missing values, and all the categorical variables are already encoded into numbers. Since we know that most machine learning algorithms cannot deal with categorical variables, so we change these variables into numbers. Since the idea behind this notebook is to learn how to work with the KNN model, we'll skip the imputing missing values and converting the categorical variables part. We have already covered it in the previous modules. So if you want to get a quick review, you can go back and watch the videos. Now moving forward, the next step is to separate the dependent and the independent variables. So in the variable X, I have stored all the features, and in the variable Y, we have the target variable which is survived. So if you look at the shape of these variables, we'll see that both X and Y have 891 rows, which is the complete size of our dataset, and X has 24 columns, which is the features, and Y has 1, which is the target variable. Now in this section, we'll be scaling the data. So as we discussed in the previous videos, scaling all the features is extremely important, especially when we work with distance-based algorithms like KNN. And so here we are using the min-max scaler, which will scale down all the features in between 0 and 1. So we import the min-max scaler from sklearn.preprocessing, and then we create an instance. Then we create another variable X scaled, which stores the scaled features from X. So let's run this cell. And since this returns us an array, we'll need to convert this into a pandas data frame. So I have used here pd.dataframe and given the variable X scaled in this, which is an array right now. And the column names for this new data frame should be the same as X, which we had previously. So once I run this cell, we'll have a new data frame X, which has the scaled features. So if we want to look at the head of the data set, here we have the same features, and in this case, all the features are ranging between 0 and 1. The next step would be to divide the complete dataset into the training and the test part. So the idea is to use some part of the dataset to train the model and keep a small part aside to check the performance of the model at the end. So we use the train test split function for this, and to the train test split, we give two datasets, X and Y. X is all of our features and Y is the target. This returns 4 data frames, which will be train X and train Y, the features and target for training, and test X and test Y, the features and the target. In the dataset, we have set any random state number 56 for now, and we use stratify is equals to Y. So what stratify does is, it will make sure that the distribution of the target class in both your training and test data is equal. So both training and test data will have equal proportion of positive and negative classes. Now we'll go ahead and implement the KNN classifier. So we first import the KNN classifier from sklearn.neighbors, and we also import the F1 score, which will be our evaluation metric for this classification problem. After that, we create a KNN instance and we name it CLF as in classifier. Then we use clf.fit, which is used to train the model. And to the model, we give the training data, train X and train Y. So this is our features and target. And then we make the predictions using clf.predict on the test data. Finally, we check the F1 score using the test predict, which were the predictions by our KNN model, and the test Y, which is the actual value for the test data. And then we print the test F1 score. So once I run this cell, I get the F1 score to be 0.678. So in this case, right now we have used the default value of n neighbors, which is 5. Let's say I change this value to 7 and run the cell again. So my F1 score changes. My F1 score has improved to 0.69. So you can actually change the n neighbors value manually, but that would be a tedious process since you cannot always try all the numbers manually. So as we studied before, we'll be using an elbow curve. So to create an elbow curve, we'll train the KNN model for different value of n neighbors and finally select the value which give us the least error. So here I've defined a function to create the elbow curve. We create an empty list called the test error, which will store the error values for each value of k that we need. To this function, we give an input k, and for every value in k, we create an instance of KNN using that value of k as n neighbors. Then we train the model, we make the predictions on the test dataset, and we calculate the F1 score. Finally, we calculate the error by subtracting the F1 score from 1 since a higher F1 score would mean a better model, and when we are trying to calculate the error, we want to see the minimum error, so we just simply take 1 minus F1 score and we append all these values to the empty list that we had, and finally this function returns us that list. So here I've defined the function. Now in this cell, I am giving the range of k values. I have taken the values from 6 to 20 and I want to check the error at every alternate value. Hence, I've set the number 2 here. So you can choose to take the values from 1 to 40, 1 to 50. You can select the range yourself. And when I set this k range, now we'll be calling the above defined function. So we call the function elbow for k, and k here is a range of 6 to 20 for every alternate values. So once I do that, I want to see the plot of the elbow curve. So we use plt.plot to plot all the values in the test, which is the test error list, and for every value of k. And these are just the x label and y label that we'll have. So this here is the elbow curve for the particular problem. We have the values ranging from 6 to 20. And we can see that the minimum is around 12 or 14, you can say. So let's go ahead and set the n neighbor values to 12 and train the model again and check the F1 score. The score has improved to 0.70 in this case. So that's how you can work on a classification problem using KNN and build an elbow curve of your own and decide the right value of k. Now let's look at a regression problem. So in this case, we have the Big Mart sales dataset. Again, we are using the cleaned version of this dataset, which means all the categorical variables are encoded to zeros and ones. So, and we have no missing values. After that, we'll follow the same steps as above. We'll separate the dependent and independent variables. Again, I have chosen X to be all my features and a variable Y as my target. Now we'll go ahead and scale the dataset. Here we are using the min-max scaler, which will scale all the values or all the features between 0 and 1. So we import the min-max scaler from sklearn.preprocessing. Then we create an instance called scaler. And we create X scaled as a new variable, which stores the transform data. And then we convert this into a data frame. So once that's done, we'll again create a training and testing part so that we can train the model on this training set and use the testing set to evaluate our model performance. Now here we import the KNN regressor, and in this case our evaluation metric I have here is MSE, which is the mean squared error. For now we create an instance of KNN called reg, and using the default values for n neighbors, which will be 5. Then we fit this regressor on the training data, make predictions on the test data, and finally evaluate the predictions using the MSE. So once I run this cell, I'll get the mean squared error value for the test data. Now, same as above, when we want to decide the right value of k, we'll create another elbow curve. In this case, I have defined another function. So we have test MSE as an empty list. And for every value of k, we create a KNN instance and train the model. Then we make the predictions on the test set and calculate the MSE value for these predictions and the actual values, and then append this to the empty list that we had. Finally, this function returns me a list that has the error for every value of k. Again, we are defining the range of k values. This time I've taken it to be from 1 to 40. You can adjust this range yourself. And then we call the above defined function. Finally, we'll plot this curve. And here we have an elbow curve for all the values of k neighbors with the test mean squared error on the y-axis. So I can see that the minimum error is approximately around 9. So I'll set the KNN n neighbors value to be 9 and repeat the same process. I'll fit on the training data and make predictions on the test data. And in this case, we see that the MSE has reduced from 1714854 to 1622957. Now, there are a few scenarios when KNN algorithm might not work well. First of all, if you have not scaled your data and your features have a very different range, in that case, the KNN algorithm would fail. So make sure you scale your data while working with the KNN algorithm. And that's all for this video. In this video, we covered how to implement a KNN classifier and a KNN regressor. Thank you.